Então, boa tarde. Desejar as boas tardes a todos que estão aqui presentes. Nós vamos falar em inglês porque os apresentadores, oradores falam todos em inglês, está prevista a apresentação é tudo em inglês e, portanto, só a partir de agora vamos começar nessa língua para todos nos entendermos. So, good afternoon. On the behalf of the Portuguese engineers, Ordem dos Engenheiros, I would like to welcome you all to this seminar about new developments on friction steel welding. First of all, I would like to thank to Sara Fernandes, that is project manager at EWF, European Federation for Welding, Joining and Cutting in Portugal, for this initiative of bringing to Portugal this issue and the presentation of a project, and mainly for the proposal for this seminar. It is with great pleasure that the mechanics specialization of the Ordem dos Engenheiros joined this challenge from the first moment. Thank you, Sara. Then, maybe the most important, I would like to thank all the invited speakers for their availability to be present here today and for the opportunity of sharing with us the new developments in this specific area. Thank you, Stephen, Santonou, that unfortunately is not with us today, Christopher and Pierre, for your time and welcome to Ordem dos Engenheiros. Finally, I would like also to thank all participants in this session and invite you to comment and put all the questions that you intend to do in the final part of the seminar after all presentations. This is about friction steel welding. Is a welding technique recommended, for example, for shipbuilding because of its high quality and suitability for automation. And as I said before, the present seminar intends to show recent developments in this area, namely for welding steel structures, representing a great opportunity to improve, for example, in this field, the productivity of European shipyards. But to better understand this project about robotic survey, repair and agile manufacture, I would like to invite Sara Fernandes to present us this project. Sara, the floor is yours. Thank you.
So, welcome all. Thank you, José, for your kind words and the welcoming. This is the House of Engineers, so I always feel at home here. And today we have a house full of engineers from different parts of the world that are combined together in this project, Resurgam project. We'll be starting today with a brief overview of the project, just for all of us to be in the same page. And then we are going to have 4 different presentations. Basic friction steel welding process applied to steel, tools and availability for industry in general. Stephen Carter will do both presentations, as we have one COVID speaker that could not be joining us today. And then we'll have the underwater repair process, and Chris will take over. And finally, we are going to have the retrofit friction steel welding head for new building fabrication with Pierre. So I'll start with the project overview. I did not present myself, but I'm from EWF. We are the project coordinators. So the Resurgam project is more or less in the middle of activities. We have started in February last year, and we are going through until the beginning of 2024. We have a budget a little over 6 million. And basically, we are trying to come up with different solutions for the maritime industry. The idea is to pick up a process, the friction steel welding process, that usually was used in aluminum friction steel welding for aluminum, and trying to diversify it for steel. and also to have two different solutions for modular fabrication and also for repairs, both in dry dock and in offshore. So this is quite ambitious. We have already some breakthroughs that we are starting now to really communicate it and disseminate it into the industry. The project is mainly for the maritime industry. Nevertheless, all the developments, both in technologies and solutions, could be easily, I think, or moreover easily translated into different industries. We have automobile industry here. We can also think about different applications for other industries, and the project business plan after the project, we are considering also different industries. So regarding partners, we have different kinds of partners. We have partners that come from the shipbuilding and maintenance industries, where EWF is also present. We have naval shipyard, which is ICER from Galicia, Spain. We also have Gizbir. We have two participants from Gizbir here today, from the Turkish Shipbuilders Association. We also have the Spanish Shipbuilding Association in Galicia, which is Aclonaga. And then we have research organizations also present here, TWI, very well represented by Stephen, Lancaster University, Limerick University, and Delft University, also with a member present here. And then, because this is for industry, we have Ford with Chris, Element 6, unfortunately not here, ESSI from Greece and Cyprus, and also Stilwell with Pierre here that is also going to present us a little bit about the company. So the main challenge for the project. The ongoing competition from shipyards around the world, mainly also with new players from Asia, and the shipyard repair process that are still expensive, require highly qualified personnel, do have high-risk procedures, and they are often inefficient and time-consuming. So we have work to do. As key objectives in the project, we are hoping to enable the use of friction steel welding for underwater and underoil welding of steel. By the end of this presentation, you all will know what FSW means. Deliver a prototype underwater under FSW head capable of robotic deployment. And also that we are not going to present today, but in the upcoming month there will be a reality. And artificial intelligence enable robotic underwater FSW system capable of performing inspection and friction steel welding underwater and in confined spaces. That could be also important for different industries. And deliver an in-yard friction steel welding fabrication capabilities for modular build, modifications and retrofitting, which will be more detailed in the last presentation from Stilwell. The outcomes of the project, so in a year and a half from now, we could be able of having and adapting friction steel welding to a new medium, the liquid one, and a new material, steel, instead of aluminium. The Resurgam digital platform to have some control on the process, mainly in offshore process. The new autonomous robotic ROV, the robotic vehicle, yeah. And the development of the new friction steel weld head that is able to connect with a CNC machine in any shipyard and to have a modular fabrication or a maintenance of a reparation of some kind of injury. So this is my presentation, a brief overview of the project. We are going now to proceed with Stephen that kindly will present us with TWI presentation and also Element 6 presentation. Stephen is a principal project leader at TWI, which is our expert in welding, friction stir welding to be more exact. He is material engineering and also composites engineering. Is a fellow of the Royal Institute of Navigation and also an associate of the Royal Institute of Naval Architects and associate of the Welding Institute. So, Stephen, would you like to proceed? We are going to start in a high note with a video.
Yes, watching a video is more interesting than listening to me. So, a brief introduction to TWI. TWI is the Welding Institute. And so, we're a professional organisation that maintains standards for welders in England and provides training courses. So, very much like the Institute of Engineers here. But in addition to that, we also have a research arm. We've got over 600 staff that specialise in doing research into materials engineering and welding. So, we actually do get our hands dirty at times and do some work. So, this will explain to you what friction stir welding is. Friction stir welding is a solid state welding process, originally invented by TWI in 1991 and widely used worldwide for the manufacture firstly of aluminium, then magnesium, copper and titanium fabrications. Under the Resurgam project, the process is now being further developed to enable the welding of steel for the European shipbuilding sector. In the short video running now, we see a test coupon of 12mm thick carbon steel being butt welded from two separate plates in TWI's laboratory. The steel plates are first secured side by side in the welding jig. The plates have simple square butting edges. There's no need to undertake a V-groove preparation for friction stir welding. The fixture is then flooded with water and the friction stir welding tool is brought down into contact with the plates. The friction welding tool is provided by consortium member Element 6 and is being developed for welding steel up to 12mm thick, in air, or as can be seen in this case, underwater. As the friction stir welding tool rotates, it begins to generate heat, softening the steel immediately beneath it and embedding itself into the steel. Bubbles of steam can be seen originating from the contact area between the tool and the steel being welded. Once sufficient heat has been generated to soften the steel near the tool begins to traverse along the joint line, stirring the metal and joining the two plates together. Once the weld is complete, the fabricated test coupon is removed from the water tank. As can be seen, the weld is smooth and free from spatter. The lack of distortion allows a 1 metre long steel rule to be balanced on its edge along the plate. A section cut through the weld shows it to be defect-free, with a fine-grained wrought microstructure. It is therefore perhaps unsurprising that tensile test pieces cut from the welded plate show the weld to be stronger than the original steel, all tensile failures occurring in a ductile manner outside both the weld and the heat-affected zones. In conclusion, it can be stated that Project Resurgam has shown to date that carbon steel up to 12mm thick can be friction stir welded, and that this is equally possible underwater as well as in air. The process produces defect-free, strong, tough welds, ideal for a variety of shipbuilding and marine construction tasks, as well as repair. For further information about the project, please contact the European Welding Federation. So that's friction stir welding in a nutshell. Basically, It's a process that was invented at TWI 30 years ago, but at that time it was invented specifically for welding aluminium, because aluminium is regarded as very difficult to weld. All that the process involves is we have a rotating tool, which is very much like a blunt milling cutter. That's lowered onto the surface of the weld area, and we then move it along. It generates heat simply by friction, but the key thing is it does not melt the steel or the aluminium. It turns it into like a very soft state, but it does not melt it, and then it mechanically stirs it together. So a lot of the defects and problems you get with conventional arc welding or laser welding or even electron beam welding, you do not get with friction stir, because you're not actually melting anything. It's a mechanized process, so it's done by a machine, so you've taken human variability out of the process, so you get a very repeatable weld. Because we have very little heat input, we get very little distortion, and one of the benefits is that because we have no liquid material, we can weld in any position. So we can weld vertically, we can even weld overhead. It doesn't cause us any problems because the weld is still solid as we're making it. If you think about conventional welding, such as arc welding or laser welding, those are actually casting processes in where you're melting the metal and casting it together. Friction stir welding is a forging process. We are literally hammering that material together with a small rotating hammer. So we get actually a forged microstructure. So it's a very strong, very tough weld. It uses very little energy. As an example of that, when Mazda introduced the process to replace spot welding on one of their cars, the production line's electricity use went down by over 80%, which is a very considerable saving. And also, because we've got no ultraviolet, no radio frequency energy being generated and no molten metal, it's a very safe process. So it actually improves health and safety in the workplace. As I said, it was introduced over 30 years ago, and it's probably one of the best kept secrets around. Most people have never heard of it, despite the fact that if you've been on a boat, a train, an aeroplane, or in a car recently, it was probably made with friction stir welding. But a lot of the companies that use it don't talk about it because it gives them such a huge advantage over their competitors. It's used in a lot of marine applications already for aluminium shipping, and people have said, we want that in steel. After it was developed for aluminium, the process was developed for magnesium, copper and titanium, because those are also regarded as very difficult materials to weld. Friction stir can weld them quite easily. And the welds themselves are strong, they're tough, they're corrosion resistant. You can automate the process and take out the variability, so it's very good. So people said, we want to do that in steel. We never envisaged using the process in steel because most people can weld steel fairly well. But once people started realizing that this would give better quality welds, they told us, you've now got to do it in steel. And part of the reason was the high quality possible. So in these pictures, what you see is in the upper image, you see a typical multi-pass arc weld in 20mm thick steel. So you've taken the fine-grained wrought plate, passed an arc welding tool through it up to 20 times, and converted that microstructure to a cast microstructure. So you've probably got shrinkage defects there, you've got a large heat affected zone, you've got columnar grains. It is not as strong as the original parent material. In the lower image, what we've done, we've passed a friction stir welding tool through the surface of that weld. That's the friction stir weld. So you can actually compare the friction stir weld microstructure with a cast arc welded microstructure and the parent material. And I think you can see that the friction stir welded structure is very similar to the parent. So it shouldn't be surprising that the properties of the friction stir weld are at least as good as the parent metal. If we look at that a little more closely, these images show on the left-hand side the parent microstructure of an S355 carbon steel. So you've got ferrite and pearlite, and you can see evidence of roll banding where the plate's been rolled. The micrograph next to it at the same scale shows the microstructure after you've friction stir welded it. And what we've got there is quite a complex microstructure where we've got acicular ferrite, we've got ferrite, pearlite, we've got some elements of bainite and even martensite in there, but it's a much finer grain structure. And what we're finding is that's giving us the benefits of all those different structures. So we're seeing the toughness of acicular ferrite, the strength and hardness of martensite, all blended together, giving us a tough, strong, very good weld. We can also change that microstructure by varying the rotation speed of the tool. We're effectively governing how much heat we put into that weld, and by changing the speed at which we move the tool, we're changing how quickly we quench or cool that weld. So if someone wants a weld optimized for toughness, we can use one set of welding parameters. If someone wants to optimize their weld for hardness or strength, we can again, within limits, we can optimize the weld to do that. This shows some of the work we've been doing. So we've been taking some big, large plates of steel, making a friction stir weld down the middle of them, and then cutting those up into test pieces, and they're being tested for strength, toughness, elongation, hardness. Some are now being tested for fatigue as well. And what we're trying to demonstrate is that the properties are consistent along the weld from beginning to end, and also determining what those properties are. The image also shows that we've done the welds in plates where we've actually prepared the weld zone carefully. So we've cleaned off any oxides, any paint, we've removed any rust and done the welds. But we've also welded some plates that where we left the rust on them, we've left oil on them, we've left all kinds of contaminants on them to find out, is this process something that you can use industrially and not have to spend a lot of money making sure that your work pieces are perfect. And what we're finding is that the welds we've made in dirty, rusty, oil-covered plates are just as good as those that we can make in a plate that's had the edges milled. The images on the right-hand side show some tensile test pieces. All the pieces, apart from the dark black ones, have failed in the parent metal. So the weld is actually stronger than the parent metal that we started with. In this case, we were seeing that the parent metal fails were going at about 600 megapascals. That didn't tell us how strong the weld was. So what we did then, and where these black samples are, every fifth sample, we cut a very sharp edge notch into the weld, 2 millimeters deep, in a 12 millimeter plate, so that we were forcing the failure to take place in the weld metal. And when we tested those, we were finding that the weld metal was showing us a strength of 760 megapascals. So the weld was 25% stronger than the parent material we started with. So if anyone's designing structures based on the strength of the weld, this potentially gives you the opportunity to downgrade the steel you're using or the thickness, because now you don't have to worry about the weld being the weaker point. We've also looked at how tolerant the process is to defects. In theory, if we do our job properly, we will never get a defect in a friction stir weld. But there will always be an occasion where someone programs the machine wrongly or does something incorrectly, and you can get a defect. And those are the welds that the classification societies want to know about. Yeah, they're not worried about good welds, it's the bad welds that scare them. So we made some welds that had got deliberate defects in them. This is a 6 millimeter thick plate, so we welded it with a tool designed for welding 5 millimeter thick material. So we were left with a 1 millimeter unbonded region at the root, which is effectively a crack. We also rotated the tool far too quickly, so the softened steel didn't have time to flow the whole way around it and consolidate against the sidewall. And that gave us a second defect at the top of the weld. Again, just over 1 millimeter in size. And we then subjected it to tensile testing and fatigue testing. And as you can see from this section through the test piece, the failure occurred here in the parent. So despite having 2 1 mm long cracks, it was still stronger than the parent material. So it shows that the process can be very tolerant of defects. So obviously, you'd never want to put a weld like that into service, but if one day one did get into service in that condition, it probably wouldn't be a problem. We can do most weld geometries. The one weld geometry that we cannot yet manage in steel is a fillet weld. We're working on that. We can do fillet welds in aluminium, copper and titanium. It's just a case of adapting the tools and making the tools better. So we should get there eventually, but at the moment we can do all these weld geometries, but not a straightforward fillet weld in a corner. But that will come in time. What we've been talking to some shipyards about is, if you can't do a fillet weld, is there a better way of actually making something like a stiffened panel? So instead of getting your large plate of steel and then fillet welding stiffening ribs onto it, why not start with a rolled T-section, so you've got a forged structure to begin with, and then weld those by spacing them apart using plate, and you can then vary the spacing as you need. So effectively what you're doing there is replacing what could be a defective fillet weld, and there we can see a fillet weld with defects. You're getting rid of that process and you're replacing it, or you're replacing 2 arc welds with 1 friction stir weld. So you're halving the number of welds you make, and these are forged welds rather than cast welds. So potentially you're ending up with a fully forged structure, much less deformation, and potentially stronger. And we've talked to classification societies such as Lloyd's, and they say there's no reason why this can't be done. One of the big problems we've faced with transferring the technology of friction stir welding from aluminium, magnesium, copper and titanium to steel is actually developing the tool to do it. Because what we're actually looking for is a tool that can stir steel. And that steel is at about 1,000 degrees centigrade. And if you think about it, there aren't many materials which are stronger and stiffer than steel at that temperature. Because the tool's rotating and being pushed through the metal, it sees quite high bending stresses and fatigue loads. And again, a lot of materials can't tolerate that. We're also embedding the tool in iron, because steel is iron, at 1,000 degrees. And at that temperature, iron tries to alloy with anything that you put into it. So the iron itself, or the steel, is trying to dissolve your tool as well at the time you're working. It's also got to be non-toxic. One of the very few materials in the periodic table that is strong and stiff at that temperature is quite toxic to humans. So that got ruled out. If you think about the amount of abrasion going on as you're rotating a tool and pushing it through steel, that will wear very, very quickly. It's also got to have a useful and predictable life as well. A lot of the early research was looking at ceramics, because a lot of ceramics can withstand the temperature and they can be inert to iron at that temperature. But they don't like rotation, they don't like bending stresses, and they don't fail predictably. And the last thing you want to do is break a tool halfway through your weld. And finally, it had to be affordable. One of the materials that people considered for using in friction stir welding tools was iridium. It's got the temperature performance, you can make strong tools out of it, but it costs more than gold. So are you going to use that in an industrial process to try and weld steel? Very unlikely. So the process works. We were always convinced we could get it to work under water and under oil. The real difficulty was coming up with a tool that could actually achieve that. And that's where element 6 came into the equation. Unfortunately, Santanu from element 6 can't be with us today because he's gone down with COVID. So I hope you'll forgive me if I carry on and present his slides to you, which explains how Element 6 started looking at developing a tool that basically was made of unobtainium. So Element 6 are part of the De Beers mining group. Their gem arm usually is referred to as De Beers, and their industrial diamond and industrial tools division is Element 6. They're a global company, they're worldwide. And they've been developing materials for the mining industry and the cutting tool industry for over 60 years. And they basically said to us, we think we can come up with a tool material that won't wear out, won't dissolve, won't break, and is relatively cheap enough to use industrially. And we were slightly sceptical because we've had lots of people tell us that in the past. And they said, no, we can do it. And so they set about doing it. So one of the materials in their portfolio are super abrasives based on polycrystalline boron nitride. And basically they take boron and nitrogen, they put them in a press, subject it to an immense pressure and heat it up at the same time. And basically they explain that if you imagine putting those materials into a small canister the size of a tin of baked beans and then turning the Eiffel Tower upside down and balancing it on top of that tin, that's the kind of pressure that they used to manufacture their polycrystalline boron nitride. So they developed the polycrystalline boron nitride, made some tools, and they made a family of tools designed for welding 6mm steel and gave them to us to test. The competing tools on the market at that time could typically weld about 5 meters or sometimes 10 meters of steel. And that was part of the problem. You never knew how good that tool was going to be and how long it would last. Would you want to start trying to do a weld that was 10 meters long if the tool had a fairly good chance of breaking after only 5 meters? So one of the important things was to prove that Element 6's tools were consistent and broke in a predictable manner. We've not actually managed to break one yet, which is good news. We've tried. So at the moment, we've found that their tools designed for welding 6mm thick steel will last for at least 65 meters of welding, and they will go through 29 plunge cycles. So that's where you drive the cold tool into cold steel, where you've got incredibly high forces and abrasion. The target was 30 meters of weld and 10 plunge cycles. So they've exceeded the targets quite easily. The quality of the welds was still good even after 60 meters of welding. Their tools work in air, they work under water, they've also worked under oil. So if you want to weld inside the fuel tank of a ship, you've now got a means of doing it. Their basic plan is to develop a family of tools that can weld steel in thicknesses from 1mm up to about 15mm. If people want to go thicker than 15mm, if there's sufficient market demand there, they will be looking at meeting that demand. This shows the level of wear on some of their tools. So we took the tools, we laser scanned them to build up a 3D image of the tools. We then did several welds with them, scanned them again, made more welds, scanned them, and measured the wear on those tools. And what we were finding was that even after 40 meters of welding, the wear was measured in microns. So that was good enough. You know, we could still make a good weld if the tool had only changed its dimensions by a few tens of microns. The competitor tools had worn out or broken at that stage. That's what the tools look like before and after welding. Apart from going black because of the heat, they're still pretty much the same. What you can do with friction stir welding is you can actually use things like milling machines to do it as well. If you're not welding very thick material and the forces are low, I said that this process is like milling with a blunt cutter. You actually can convert milling machines to do this, which you'll hear about later. One of the real reasons that Element 6 are so good at making these tools is one of their major products is synthetic diamonds for industrial cutting tools. And as luck would have it, the process that they use for making synthetic diamonds is almost identical to the process that's needed to make PCBN. So they've got all the techniques in place and all the knowledge in place to start out by identifying which powders they need as their precursors, how to blend them, how to pressurize them, heat them, and convert them into tools. So they really are a good partner to work with and manufacture these tools. We work with them, provide them with feedback. They then reformulate the tools if necessary. And as we've already mentioned, their aim is to have tools available to weld up to 15 millimeters of steel by the end of this project. And we've actually seen that they've got a prototype 15 millimeter tool already, and we're only halfway through the project. So I don't think we're going to have any problems meeting that target. So that's a quick overview of the basic process of friction stir welding and the tools that are used for it. So I'll now hand over to Chris, who will explain how we're actually going about welding underwater with these systems.
So we are now proceeding from the friction stir welding processes into the two outcomes of the project, one for the offshore and the other one for the dry dock. So Chris is an operations manager at Fort Engineering. He has quite an extended experience in different sectors of activity, as the nuclear, the oil and gas, marine, civil, and working with public and the private sector also. So Fort Engineer is in the process for the development of an underwater solution. And Chris has a big challenge ahead of him.
Thank you very much. Thanks, Sarah. And thanks, Stephen, for giving us a good overview of friction stir welding, and hopefully you've all got to grips with that. So I'll give you a quick company overview. As Sarah just mentioned, we're quite a small engineering company, but we work in the nuclear sector. Where we're situated in Cumbria in the northwest of England is very close to Sellafield nuclear site, and we've done a lot of our work with Sellafield in decommissioning. We also work with oil and gas and renewables, as well as a number of these research and development projects as well. So our problem statement. The difficult thing we have to try and solve is that we've got to develop the concept and the prototype hardware system that can enable us to do remote underwater friction stir welding. And that's pretty much what we were given at the start. So that left us with a little bit of ambiguity. And there is another part of our work stream, which is the development of the data transfer and communications, and one of our partners, J4IC, are going to be heading up that bit, but our part is that dealing with the hardware and making the hardware. So we have a number of challenges associated with that, and I'll try and take you through them because I think it helps set the scene and understand the challenges for the project in general. First and foremost, as you've heard, friction stir welding is carried out in the horizontal plane. So you've got the use of gravity to give you that Z-axis, that plunge force that Stephen was talking about. So we haven't got that luxury. We've got to do it in the vertical plane, which is difficult enough because we've then got to try and work out how we get the Z-force axis to start that weld. So that's one challenge. We also have the weld parameters, which Stephen's worked really, really hard, and TWI have to try and reduce the weld parameters as much as possible for us. But we need about 40 kilonewtons of Z-axis loading force to initiate that weld, and in the vertical plane that's fairly difficult. Not to mention now it's underwater as well, so the whole machine has got to go underwater, which has its own issues. So there's water ingress, visual feedback, weld quality issues that might come with that, but another one of the challenges. Another challenge is the control. So we have to deal with X, Y, Z control. So much like a normal miller machine or something of that ilk. And we've got to attach this machine to the ship's hull, or in this case for the challenge, a mock ship's hull, which I'll come on to explain a little bit later on. We've also got to be able to control the speed of the tool and the linear motion of that as well. Everything will have to be marinized, and we've got to try and reduce the weight of the machine. So we need something strong and robust, yet lightweight. So that gives us another challenge. But we're going to try and get around that with some neutral buoyancy. And finally, as with any of these consortium-led projects, we've got logistics of working with people from all over Europe, which is fantastic. But this is the first time many of us actually met face-to-face in over a year and a half. So there are challenges associated with that, and chuck a pandemic in there as well. So how do we actually do it? So at Forth Engineering, we follow a fairly strict project life cycle, and we do this with all our projects, and Resurgam was no different. So the first part is optioneering, and this is where we look at do a texture analysis. So we were given a grant agreement that was drawn up at the start, and we would just analyse what is our challenge within that, which I've tried to explain for you. We then look at our functional means analysis. So what are the functions that the machine actually needs to be able to complete and do? After that, we go into concept selection, and the way we did that is we worked with 3 or 4 of our engineers and separate designers who were all given the same brief, and they would go away and come up with a concept on their own. That's to try and get rid of any sort of collusion and try to give us as much variability as possible when we came to actually choosing the right concept. We would then pit these concepts against each other with a Pew matrix, and that's where we would compare the functional means, so what is the actual machine, the robot, going to do, against the non-functional means. So the nice to haves: is it easy to operate, is it easy to move, is it easy to attach to the ship's hull? And it's actually those things that you are comparing, because you would expect that after you've done the concept design, those 3 or 4 engineers have met the functions. Each one of their concepts does do the functions. It's the other stuff that allows us to make it easy and hopefully take the project further into commercialisation. Concept design is where we start our technical drawing, and we use some CAD drawings, and this is also coincides with the design risk assessment to justify any design changes or any design decisions that go throughout the project. This is really, really important. Because when we feed back to the consortium, we can explain our movements and why we've made certain decisions on certain technology choices. Then we start with basic equipment selection, and then there's a design review. So at that concept stage, we have a design review where we will do that internally, and we will try and pick the design to pieces to give it the best and look at the failure modes potentially. That gives us the best chance of making it successful. We then go into a detailed design, and the detailed design is obviously trying to detail all our components. That's where we start to put the nuts and bolts together and really try to make this project work. We'll then do another design review, which is in more detail, and finally we look at some consultation. So that's where we do a peer design review with our colleagues such as TWI and Stirweld, and they can start to look at our designs and see whether they think, from their experience, they think it will work, or there might be some faults in there. That allows us time to go back and correct it and change it. Then we have the manufacturer, and actually that's the easy bit. Building it's the easy bit. The first 4 steps are the difficult bit. And I know the consortium is impatient with me because we're trying to get to that point, but we are very, very close. So building it's the small part, but actually the work beforehand gives us the greatest chance of success. And then finally, implementation. So we will be testing this in our pond facility. Because we work in the nuclear industry, we have a large pond facility, which I'll show you a picture of later on, and we're going to create a mock ship's hull in there and test it in that facility. So we'll do an initial test, which is just within the consortium, the Work Package 3 consortium, in January and February next year, and then the final test will be at the end of the project, where the whole consortium will come to Cumbria and see it, hopefully. So that leads me to the next bit. So when we started off doing this, we had to try and understand the different systems associated with the challenges mentioned. So there are 3 main things, but this outlines a few more. But we've got the XY navigation system for the weld head. We've also got the ship's hull, like I've just mentioned, the electromagnetic base, or how we're going to attach it to something, a control module, how are all these functions going to be controlled together, and power systems, and finally the actual weld head itself needs to be made, designed and built. So we did this to try and understand the interdependencies between the partners, because one of our challenges is we've got lots of different partners chucked in the mix. One of the first things we wanted to, before we went into design, was work with TWI to understand the parameters. Now, I've got some tool parameters there, I won't read them all out, but rotational speeds, it's got to be able to start up at 800 RPM and then it'll drop down to 200 RPM. All of this allows us to choose our technology appropriately. It also means that we are trying to get these parameters as low as possible to help us with our design. And that's what Stephen and we've challenged TWI to do, and they've absolutely risen to the challenge and done so. Like Stephen said, we're going to be conducting a lap weld, and we're actually going to be doing it in 4mm thick steel with a 6mm tool. That means that there'll be 2mm penetration into the parent metal. The Z-axis force has been a bone of contention, trying to get that as low as possible to make it as easy as possible for us to design the tool, and we've managed to get that on our TWI. I've managed to get that down to about 40 kilonewtons, and we obviously have a factor of safety in there as well, which we'll have to use. So the three main things, as I mentioned, are attachments to the ship's hull, the weld head actuation, so the functions of the weld head itself, and the control of all dynamic and static parts. So, the technology section, to attach it to the ship's hull, we've gone down the route of electromagnets, and that's part of what was in the grant agreement, and we've done some testing with one of our supply chain companies called Rotary Engineering. Each magnet provides 70 kilonewtons of force, and when you see the design of the machine itself, it has to be able to cope with that Z-axis force of 40 kilonewtons with the 30 kilonewtons as the safety factor. But at any particular point on its weld path, it has to still be able to do that, because otherwise you could get deflection or distortion at any point, and we have to maintain a solid weld. One of the challenges we had around the magnets is actually mounting the magnets to the frame, and we've had to get some bespoke fittings made on the magnets themselves. Should this be taken further to commercialisation, that's also going to be a bone of contention, because the test that we're going to be doing is on a flat plate, but obviously on a ship's hull it will start to be curved. Something that isn't out of reach of out of the realms of possibility, but it's certainly an extra part to think about. So the next section was actually understanding how the weld head is going to move. So standard XY Cartesian systems such as Miller machines are great, and they're tried and tested in that horizontal plane, and yet in the vertical plane we thought there could be some deflection or distortion. Not to mention there's quite a lot of functions involved with that, which make it complicated for control. So we looked at some of the supply chain in the past, and we've looked at tracked mounting systems. This reduces the risk of that deflection or distortion, but it allows you only to have a fixed patch size, which could be seen as a con, but we feel that you could have a number of these tracks, and once you've got a number of these tracks, you could have a range of different size patches, allowing it to do so. We feel this will provide us with a tool that we know is going to make sure it's going to be strong enough to hold the weld head in place, but also makes it as easy to control as possible. The next thing was the technology selection itself around control and motors, and we went for hydraulic over electric because the optioneering process favoured that, but obviously they're easier to marinise hydraulic pieces of kit than electric pieces of kit. Avoiding electrics in water is always probable. There are also proven off-the-shelf technologies that are done with subsea control companies that have spent millions and millions of pounds and millions of dollars to redefine these systems. And we've worked with this company before who have got off-the-shelf bits of kit that are allowing us to have the right number of functions. And we just thought that in the context of all the challenges we've got, that was one we could take away from ourselves and use some help. So as I mentioned before, it's going to be tested in the pond facility, and this is the pond facility where I'm from, back in the northwest of England. I think the actual building, or the pond itself, is about 22 metres long, 10 metres wide, 6 metres deep, and it costs a lot of money to fill it up. So the drawing on the left-hand side shows the frame, and the frame we're going to build will go over the side of the pond wall. It'll have its feet on the floor on this side of the wall. It'll also have feet at the bottom of the pond as well. That's to spread the loading, because we're going to have a decent amount of loading with all the machines there, and we didn't want the pond wall to fall over, which was important. So on top of that, you'll have the mounting of the actual ship's hull, or the mock of the ship's hull with the damage, and you can see the hole on the plate there. That's mimicking the damage at the moment. The damage won't quite look like that, but it was just putting some drawing together. Our machine will then have to mount to that. And this is the first sort of view of our, we're in the middle of detailed design at the moment, and I'll explain some of the problems we've had with that, but also some of the successes. So this is our welding head. You can see Element 6's tool at the bottom end here, right the way through your bearings and your shaft, right the way through your casing and into your hydraulic motor at the top end. Now, one of the challenges we're facing just this week actually is the hydraulic motor. So to get the parameters needed and the low speeds that we need to actually move the tool, we're struggling with the motor that can do that. That size of motor currently in our design is quite small, which is quite nice to use, but the one we're currently looking at that can actually do it is a lot bigger than that, which may mean we have to change the design of the frame, which you'll see on the next slide. This gives you a view of the head all put together. As you can see, you've got your motor there, you've got your tool at the bottom of the first image. You've got your two hydraulic rams being able to provide that Z-axis actuation force. Okay, and you'll soon see the magnet clamping facility which allows you to clamp against that. This is the track itself. Okay, so we've gone for a circular track which gives us a stronger, well, it gives a more stiffness to be able to conduct the weld. We've got a mounting plate there which is driven around by a gear which is marked on the second image there, on the first one next to me here with the blue things, with the blue gearbox. That's going to drive the head round the track. You've got your mounting plate there and the head itself just sits underneath it with the two rams in yellow there. We've gone for a circular weld, like I said, because it makes it stronger and it was easier to be able to run the actual tool around the circular track than it was to run it around the rectangular track. There's no reason we don't feel that that would make any difference to the actual weld itself, and speaking to our colleagues within the consortium and within the shipbuilding industry, we don't feel that it's any issue as long as the weld goes right the way around that patch. And this is the first concept or detailed concept design of our actual tool. So you can see there's 4 magnets there, each capable of producing 70 kilonewtons of force. You've got all angles here, so you've got the underside, which is this picture closest to me here, and that's where the weld will be carried out with the tool going around the track in that distance there. You've then got the underneath the plate there, which you can see the actual mounting and the gear driving that around the track. And then finally, you've got the plate on top with all the stiffening bars to make sure that the tool is as stiff as it possibly can be, allowing it to conduct and complete that weld. As I said, we're currently in detail design. There will probably be a few changes to that, but that is pretty close to how it will look, I feel, going into the next 6 months. So the next steps for us, we've got to go through our detailed design review and then our peer review with the rest of the consortium members, and then material procurement. And with the world as it is at the moment, material procurement is becoming more difficult, and I'm in a really difficult situation at the moment with having to procure materials before we finish detailed design in order to try and meet the deadline of the project. But it's certainly a good position to be in, but we're actually moving things forward quite quickly at the moment. And then it'll be manufacturing it and testing it in January next year. So I hope that gives you a good insight into the actual tool itself. I'm sure there'll be some questions at the end, but thank you very much for listening, and I'll pass you on to Pierre.
Okay, thank you, Chris. As I said before, easy task, huh? So we are going to hear now from Pierre Mas from Stilwell, a different solution. Less water, no need of magnets.
Yeah.
So a dry dock solution for an existing CNC machine in any shipyard available. So Pierre is a mechanical and industrial engineer from Stilwell. And he does have a very important characteristic for this project, as we are from different countries around Europe. He already has a previous experience as a globetrotter and he's a product engineer in Stilwell. So Pierre, thank you.
Thank you, Sarah. So I'm French, so you will have to excuse my English. It's not as good as Chris and Stevens. So I will do my best to firstly present my company. So my job in this project was to the retrofitting of a FSW head made firstly for aluminum to a FSW head for steel. So I work for Stilwell, which was created in 2015, and a little bit more than 20 persons work in this company right now. And we have installed around 22 FSW heads worldwide. So the main activities of Stilwell is to design and manufacture FSW heads for aluminum that are to be mounted on regular CNC machines. So the main idea is for our clients who are interested in FSW for aluminum is to provide a product that turns a regular CNC machine into a FSW machine. So it's of course less money because you don't have to buy a specific machine for aluminum. We also design and manufacture FSW tools that are to be mounted on our FSW heads. And as we want to provide a full support for our clients, We also design and manufacture clamping tools because, as Stephen said, there is a lot of forces involved in the FSW process. And we also do test and determination of welding parameters for every new project because, as Stephen said, every FSW weld need to be correctly parametered. I'm talking about the rotation speed, travel speed. Thank you. So we have 2 engineers that work daily on those tests to provide the best support for our clients. Here are a bit of our references. So our main activities goes to automotive and aeronautics, but we also have projects in space and renewable energy, as we weld gas tank and those kind of things. So this is a quick overview of our aluminum FSW head. So you can see the blue part is the fixed cradle, and the yellow part is the slider that goes up and down into the fixed cradle, providing the force management. On the top of this blue part, there is the interface, which is a specific design for every CNC. And we use a shaft to convert the rotation of the spindle from the CNC machine to drive into rotation the tool holder and the FSW tool. So a quick overview of the state of art at Steerweld. So as I said, our FSW head is designed to be installed on any CNC machine. The rotation of the FSW tool is done by using the spindle rotation of the CNC. And we use a soft shaft coupling inside the FSW head to prevent any damage on the CNC spindle. And as I said, we also design custom interfaces to fit any machine by keeping the head standard. So on the actual FSW head, these are the specifications of the product. So the main force that will be interesting in the FSW process would be the force on the Z-axis, so the forge force, and the force on the X and Y axis is proportional to the Z forces. Actually, the force on the Z-axis is about 25 kilonewtons. The rotation speed goes up to 8,000 RPM, and the torque goes around 50 Newton meters. We have a temperature measurement on the slider part, and the stroke of these sliders is about 25 millimeters. As the temperature to weld aluminum on FSW process is not really high, we just have an air cooling on the FSW tool and very simple water cooling inside the slider. So those are the specifications for the retrofit of the FSW head to a steel FSW head. So the maximum forces on the Z-axis we want to reach is around 50 kilonewtons, and as I said, the X and Y are proportional, so it will be increased also. The rotation speed will be lower than for the aluminum, so we will go up to 3,000 RPM, but the welding torque is much higher, about 3 times the welding torque for aluminum. So it goes up to 150 Newton meters. Of course, we will keep the force measurement during the welding, and we will have other temperature measurement all around the product, because the main challenge here is the temperature to weld steel is much higher than aluminum, so we need to prevent any damage on the FSW head. So there will be a measurement on the slider as on the first product, but also on the fixed cradle, and we developed an add-on that could be mounted on the head, so we can measure the temperature directly inside the FSW tool. The stroke will be also increased on the Z-axis up to 50 millimeters. We will keep the air cooling on the FSW tool, and we will improve the water cooling on all the product. So we will have a little bit more complex water cooling circuit inside the slider, and we will also provide water cooling inside the rotating shaft. Since 1 year now, on every new project, we develop a specific human-machine interface. So we also will have rotation speed measurement on the rotating shaft, as currently we just use the info from the CNC machine. This is design differences between the two products. So on the left side, you can see the differences in size. So of course the small one is for aluminum, and the big one is the Resogun project, made for steel. So you can see the FSW head for steel is as twice as big as the aluminum FSW head. So the main design differences beside the size are the sliding elements that provide the up and down movement of the slider. So of course it's not the same scale for the views, but you can see that we switch from a system with 2 rails with walls between them to a system with ball carriage and rails, which are very much stronger. As I mentioned, we also reviewed totally the circuit of water cooling inside the piece. So on the left side of the slide, you can see the very simple water cooling circuit in the current FSW head, and the 3 next pictures explain the water cooling circuits inside the new head. So on the middle here, this is the fixed cradle. So you can see that the water goes all around the part, and this part is the rotating shaft, with basically almost the same concept for making the water go through. The main challenge was to make sure that the water still goes through when the part is in rotation. So we use specific, I don't know the name, is it gasket or sealings? Yeah, those are sealings to make sealed chamber filled with water, and then the shaft rotates inside those chambers. So I mentioned the rotation speed measurement. So this is quite simple, but we just machined slots into the rotating shaft and implant a rotation sensor just in front of the slots. So the next steps for this project, so the drawings are currently being done for every part for manufacturing. And then we'll have to identify suppliers for specific parts, as there is deep drilling for the water circuit, and also gasket cutting. And then we will manufacture parts and do the assembly of the FSW heads, and do every test and fine tunings to make sure that everything goes well. Thank you for your attention.
Merci Pierre. So this concludes our presentation. We had quite a few highlights presented here, quite a few problems also presented here, and we would like now to open the floor to some questions. Otherwise, I do have questions. Yes, please.
Thank you for the good presentations. First, do you foresee having a bigger would be a challenge in terms of commercialization? So, in comparison to aluminum, you're producing a larger type. Do you think it's going to be seen as a stand back from who is commercializing?
Yeah, would you like to answer this?
I'll try to answer. Well, I'm not the most competent person to answer this question, but yeah, I think it will be a success in commercialization because we, as I said, the FSW head developed by Steerweld has a great success because of its price. So I think, well, it was part of the project to have a very low price product. So I think if the tests are a success, I think the commercialization will be a success too.
And do you plan after the project to include this as part of your products on your catalog?
I will have to ask to my CEO first. I have no idea.
Okay, thank you.
Thank you. Any more questions? Yes.
First of all, thank you for the presentations and for the topic. It's very interesting. I want to address a question to Christopher about the challengings of applying the process, difficult process, even underwater. So how do you plan to cope with the start and stop defects? Because you don't have a start run and an end run on the process.
So on the patch itself, we don't believe it's going to be a problem to have a start run and an end run because it's not a structurally sound weld in that sense. It's meant to be a patch that goes over some damage. So it was something that we've addressed in the past, and we had a previous project where the very same issue came up, and to deal with that, we basically created a ramp within the steel. So as the tool was being drawn out the steel, then the defect would be in the ramp and not be in the actual structural part of the weld. So if that was a problem, then we could deal with that in the same kind of way. But at the moment, we don't believe that's an issue. But thank you for your question.
Thank you.
Thank you. A third one? No? So, one of mine? No, not yet. I've got difficult questions.
Good afternoon. Thank you very much for your presentations. My question is more related to the microstructure. You referred that after welding, you mentioned that you did also some fatigue testing. And I was interested in knowing if, because you did not mention in this presentation the sensitivity to corrosion. And I was wondering if the process itself within steel, depending on the medium for the heat diffusion, if you're going to have some sort of residual stress building up in the welds, and of course this would accelerate the corrosion process.
The simple answer is yes, we will get residual stress. It may not accelerate the corrosion. We've done some testing, and by its very nature, corrosion testing takes time. What we find is that when we're doing the welds, because we're compressing the steel when it's in a soft state, and then it's basically sets in that position, the residual stresses are primarily compressive. That is part of the reason we're getting good fatigue performance. What work we've done so far on stress corrosion and corrosion resistance in general as showing that we're actually getting very good properties and the weld itself is very resistant to corrosion. That may be down to the fact that it's a fully autogenous weld. We're not adding a filler, we're not actually boiling any elements off. So the weld metal has the same chemical composition as the parent material on either side of it. So we're not getting a galvanic couple across that weld. We're also finding that the weld surface is slightly hardened. And so when we've done erosion corrosion testing, for example, for the inside of a pipeline, we're finding that we're not getting pitting starting in the surface because of erosion. Therefore, the corrosion process itself doesn't start as quickly and progresses quite slowly. That is very limited testing because we're only, into the earliest part of the project. There's a lot more testing to be done, and Neil, who's just hidden away at the back, has got the delightful task of doing about 900 sample tests. So hopefully in 18 months' time we'll be able to get a much more definitive answer. But so far, what we're finding with friction stir in steel is that it sounds too good to be true. Because when you tell someone we've made a weld which is stronger, tougher, more fatigue resistant, harder and more ductile than your parent material, they tend to say, no, I don't believe that. And we're saying, well, we're having to rewrite the textbooks because we're not doing it from a weld that's been in a molten condition. It's solid state forging.
Is it surprising?
Well, I don't have experience in steels, but I have done some work with Thomas in the heydays with aluminum and aluminum alloys. That was those days 30 years ago, maybe, or 20 something. So, but I have actually another a follow-up question. There is some sort of available commercial equipment, not only the adaptation of the drillings, but ESAB, I remember, was a partner. Do they still have this sort of offer to the industry? Because I lost a little the track of the evolution.
Yes, there are many companies that will do bespoke friction stir welding machines for you.
Okay.
What most of those won't tell you is that you can probably do it for much less cost by converting an existing milling machine, which is where Pierre's company comes in and converts those machines. But if you go onto TWI's website, for example, there's a list of about a dozen companies that specialize in making friction stir welding machines, but they tend to be quite big and expensive.
Niels, do you like to add something to the testing part that is starting? No?
We are in the process of doing we are in the process of doing the fatigue tests. The fatigue tests that we've been doing now are on. We started with an initial underwater weld that had a defect in it. Sorry, let me just free my hand up a bit here. The initial tests we've been doing were on those underwater friction stir welded joints, which had a defect in it due to a worn tool, which was something that we had known beforehand, which is something that Steve had mentioned to us already. And the testing that we are now doing is dedicated testing on the testing matrix that we've set up, which will be S335 steel, S460 steel, 6mm thickness and 12mm thickness. And like Steve said, we hope to be able to say something, and I'm sure we will in a little more time than we've had up to now. So get back to us.
Okay, thank you. Any more questions? No? Steven, can we have a weld in a curved surface?
Yes, most of the time at TWI we're doing welds on flat plate because we're producing tensile test pieces, Sharpie impact test pieces. Real world components are very rarely flat. So if you go into industry which is already using friction stir, you will see that they tend to use robots to do it and make many 3D welds. So, for example, if you look at an aircraft fuselage or a train or a car, they're not flat. So yes, you can do a weld in 3 dimensions, 2 dimensions. It is quite possible.
Thank you. So we've mentioned that we've started this project a year and a half ago. We've planned for it for more than 2 years. By that time, no COVID, no war. Everything is different now. Today is the first time we are all together in person, so that's pretty amazing. So a few things change from the planning to the implementation of the project. Chris, because you are having trouble with this, how do you characterize the main issues, and how are we trying to go around them?
So, as I said, some of the main issues, of the project, like I tried to describe in there, are just around technology selection, I think, at the beginning. But as we're coming through the detailed design stage now, it's more about material procurement and dealing with material procurement. And as I said, we're in a kind of a strange situation. Normally you'd go fully through your detailed design and then you'd finish that off, we'd have that peer review, and then we'd be able to start ordering materials. But with things in the scarcity of materials at the moment, and companies that, like, for example, the track lead time for the track can be over 5 months, I think they've said, before they can get the right materials to get to us. There's not many companies who can do what the company have done, and they've worked with us in the testing. So I'm in a position where I'm having to look at trying to order some of the longer lead time items before we finish detail design, which obviously carries a risk with it. However, I think it's a calculated risk. I think it's a risk that I've very much mentioned to the consortium. We have discussions around it and try to deal with that in the best way possible to make sure that the project gets as much value for money as possible as well. So, and we're doing that with as fewer items as possible. The magnets is another one. The components needed to make these magnets, they're fairly large, but also the components are fairly difficult to get hold of. And the lead time for that, I've been advised, is around 18 weeks to get those. And considering we're supposed to be able to do a test in January this next year, then it doesn't leave me a lot of time to get the detailed design done. But it's those two are the main two components. Steel is a very volatile market at the moment as well, with many steel companies not holding the price for over 12 hours, that's it, and then they change the price again. So we're in that position quite a lot at the moment as well. But they're just the real world problems that come with the challenges of any project. And to be honest, it's part of it and part of the fun, I suppose, part of the challenge that we have to do to try and make it work. Some of the main challenges around it is just the complexity of the different systems that are needed. The clamping forces, obviously, you've got to have your linear speed, you've got to have your rotation speed, you've got to have the torque, you've got to be able to produce the amount of force to do the weld, and that is a significant challenge. And I think that at the start as well, I think that there's obviously risks around the commercialisation of it. We're doing it on a flat plate, as Stephen said. If we want to take that to commercialisation, we have to be able to do it on a curved surface. I think we can, and I think we can still do it based on the ideas and the concepts that we've drawn up now with some adaptation. One of the biggest changes for me would be potentially looking beyond magnets and looking at something like suction cups or stuff like that might be able to be used, which could be something that in the future might be cheaper and a better alternative to commercialisation, which I'm sure we'll discuss over the next few days. So.
Thank you. And that's my next question for you, and also Pierre, probably. When is commercialization a reality?
I think first and foremost, it's about proving that we can do what we've set out to do. So if we can get a preliminary test in January this year, that'll give us an idea of how close we are. And that gives us 12 months before the end of the project to get it to that position. I'm fairly confident we will conduct a weld on a mock ship's hull in water, and I'm fairly confident we'll be able to do that. I think the reality comes when you're looking at taking it onto water and onto the ships. You've got to deal with the power consumption. We're going to have access to generators on land, and yes, ships are floating power stations. You've got lots of power there and all the rest of it, but it's still a challenge in itself. The one thing that hasn't been addressed in this project, which would have to be addressed as well, which definitely could be done given budget, would be the patch deployment. So for the test itself, we'll have the patch fixed in place and be able to go around it. The beauty of friction stir welding, as Stephen's pointed out before, is that you could tack a patch on, or you could bolt it onto the side of the ship, because you can weld right through your bolts. which is an added value. You don't have to take them out; it doesn't cause any damage. So that's something that we've looked at to be able to take to commercialisation too. So I think if we get to the end of this project, it isn't a huge distance away, but there are those 2 or 3 things that I think we'd have to really start to put some time and effort and funds behind to get it right.
Okay. Pierre, your job is easier,
Yeah,
so
yeah, it's a lot easier. So, what can I say?
by the end of the project, will it be ready to go?
Yeah, because as I mentioned, we are currently doing the drawings of the parts. So within a few months, they will be manufactured. A few weeks, sorry, they will be manufactured. So I'm quite confident that by the end of the year, we will have a product to show and to test.
I think to add to that as well. Although it could be commercialised, we're going to have 2 products there that could be used in different industries. It isn't just necessarily the maritime industry that they could be used, and I think that's really important. I'm sure Stephen has had inquiries. We've already had inquiries from the nuclear industry, for example, about friction stir welding machines that can do those things. Pardon?
The oil and gas industry,
Yeah, the oil and gas
wind farms
yeah,
also?
absolutely. So the oil and gas, the wind farms, the nuclear industry as well, and we will have 2 bespoke tools effectively that can do those things and do it in different industries. So I wouldn't want to limit it just to the maritime industry. I think the actual developments and the learnings from this project could be taken into all industry.
Okay, so we'll have time to disseminate it among shipyards associations. We have one here today. Would you like to add something to the discussion? An overview from your members, perhaps just a minute until the mic arrives.
Sorry. Hi.
Oh. Sorry, my question was for the Turkish shipyard, but
Okay.
feel free
So
to.
I'm just adding 2 notes regarding the ship repair. It's regarding the thicknesses. Usually thicknesses on ships are around 25 millimeters. And second is the fit up of the plate for the weld, the fit up. So cutting the existent and putting the new one, and the fit up of the new plate that is going to be inserted. These are 2 points that I believe it's important for you to address. Thank you.
Thank you very much. As Turkish Shipbuilders Association, in fact, we consider that the project is really challenging. We have 84 shipyards in Turkey, and most of them are interested in new building and also repair and maintenance, both, I mean. So we have many dry docks and floating docks also. But I think this project is really interesting because we can make some weldings and repair and maintenance without using floating docks at the end, I hope. And for building the blocks, for example, the stiffened panels, so it might be also interesting. But unfortunately, when we evaluate the situation for milling machines in shipyards, unfortunately, we couldn't find more. Only one of our manufacturers have milling machine, very big milling machine, because they bought it for a submarine construction. So I think also it might be interesting for military and naval ships. So we will see, but at the end we would like to do all of our efforts to disseminate all the project outputs to our members and also getting some information from our members. Thank you.
Thank you. Chris, will you address the question?
Yeah, so around the thicknesses, I think in the constraints of the project, we've gone down because it's not structural and it's a patch, and it basically allows the ship to be able to move on and move forward. And what we're trying to prove is that concept. So if we can prove that concept in the pond, there's no reason why we couldn't go to greater thicknesses. But obviously what I'm dealing with there is I'd have higher Z activation forces, therefore I'd have to have a stronger way of clamping the system to that. And for the purposes of the project, we felt that being able to do it at the thicknesses we've got to prove that concept would mean that yes, we don't have to spend loads and loads of money to be able to do that. We can then do that with the money we've got, prove it, and then say, right, now we can go and develop it further. And so yeah, it's definitely something that's considered around the thicknesses. for sure. The patch deployment is the other thing, and how you would move the patch into place. And we've got some initial concept designs of that, but it wasn't part of the scope of the project, and yet it would be to commercialise. That would be one of the main two things would be how to put the patch in place, and how to deploy that patch would be another research in itself. But we have already got some concept designs on how we would probably do that as well.
Can I just add a comment? One of the things that we've seen, as well as the interest from commercial shipping, the naval side are very interested in friction stir welding. They are particularly looking to move to much higher strength grades of steel because they want to reduce the weight of their ships. They also want to reduce distortion as much as they can. And friction stir welding gives them the opportunity to basically weld some grades of steel which they currently wouldn't want to arc weld because of the difficulty. They can reduce the thickness of the steel they're using, and they're talking about welding 4 and 6 millimeter plate for hull cladding, for example, which is quite thinner than a lot of ships use. They want to do that for good reasons of their own, but they've found that if they try and weld those kinds of thicknesses using arc welding, they get a much enhanced radar signature because of the distortion. Friction stir welding takes that away, and they're quite willing to pay a premium price not to show up on radar. So there are lots of interesting things that friction stir can do beyond the obvious.
Yes, it's just, is it clarified? Would you like a follow-up question? No, from, okay, thank you. So next question, please.
So regarding the thickness, if we have something like 30 millimeters, it's possible to weld from one side and the other side with a 15 millimeters tool?
Yes, if you have access to both sides, you can weld twice the thickness. That actually has shown to have some benefits. When we've done double-sided welding, we've seen that the properties of the weld can be improved. Distortion is reduced even more. It's not a process limitation. It's down to the tool technology. In aluminium, people have welded over 200 millimeters of thickness. So it's not a process limitation. It's how strong can you make that tool. So basically, we're saying to element 6, look, we can weld aluminium that thick. Can you give us a tool to do that to steel?
Thank you.
Yes, we have another question.
Will we do it with a single pass and with access with two tools, one of both sides, or would you access the welds in a pass on one side and the pass on underneath?
We've looked at doing it in both ways, and there are advantages and disadvantages to both. If you weld the component from one side and then you can turn it over and weld on the other side, you then only need a relatively simple machine. If you want to try and weld it from both sides, you need a machine with 2 spindles, and you have to be able to support the material that you're welding, but you're getting rid of the need to turn it over. Ships aren't easy things to turn upside down. We've also found that technically, if you weld from both sides at the same time, you can reduce the forces because you're putting the heat in from both directions, and you can play around and do some clever things with the tool design and the flow patterns in the steel. You can actually reduce the forces, which Chris likes the idea of, because then he can make a smaller, cheaper machine. So a lot comes down to trying to find out what the final properties of the weld are required, because we often say at TWI that we've got the easy bit in this project. We've only had to overcome the laws of physics. The other people in the project have had to overcome the laws of economics. We can sit there and say, oh, these parameters will give a perfect weld. And then Chris phones me up and says, can you specify that with only half the rotation speed? Because it'll make my electric motor much cheaper. And so that's what we do. We then have to revisit it and say, okay, we will accept a slight change in the weld properties because it makes the machine affordable. And, Neil's asked us, can we make welds with defects in? And people like Lloyd's and so on said, oh yeah, We want to see welds with defects in, and as scientists, we don't want to create welds with defects, and we want perfection. And yet Lloyds say to us, we don't worry about the good welds, it's the bad ones. Make lots of bad welds and let Niels test them.
Okay, thank you for your participation and for your answers. I've got here one, maybe two questions, very simple. This is not my field, okay, welding is not my field, but can you weld only in a straight line, or you can make some curves when you are welding? And if it is limited to a certain area, for example, if you have to do a welding in 20 meters, is it possible?
Yes, we can weld, as long as you've got access to the surface to weld, you can weld almost any shape. You know, far cleverer people than me program robots to do 3D welds, you know, all the way around the circumference of something. We've actually, as Chris will know, we had a project where we had to weld inside a pipeline. So it was a 1 meter diameter pipe, offshore, subsea. And Chris had to design a machine that could go and do a 3D weld in a machine like inside those conditions, with the oil still flowing through the pipe. So, as I said, we had it simple. Chris had the hard bit. So, yes, we can weld in any position, any shape.
Is it different when you weld underwater and under oil? There are differences?
I'm sure Stephen will be able to give the detail of it, but I think... Sorry, Stephen's probably a better place to answer than me, but yes, I'm sure there are different properties. As I understand it, in my limited knowledge of Stephen's world, is that when you start the weld, you're creating a seal anyway, so it shouldn't necessarily matter what the material is under that. You don't have any of the water or any of the oil underneath the weld anyway, so I don't think that matters, but I'm sure Stephen can elaborate.
Yeah, that's the simple case. Once that tool is embedded, the surrounding environment doesn't really matter, which is why people are interested in welding using friction stir in explosive environments. You know, we've had some inquiries from people that were asking on behalf of a friend, because they don't have this problem, but they know someone that might. Can we weld inside an oil storage tank or a fuel storage tank if, for example, it had a problem and they needed to put a patch on? They don't want to drain the fuel out. They definitely don't want to go in there, drain the fuel out and strike up an arc. A friction stir welding robot could swim down to that and weld it while it's still full of fuel. Theoretically, because no one really has that problem. The big problem we have when we were asked if we could weld under oil was, the clue is in the name, friction stir. We rely on friction to generate the heat to soften the metal. And our question was, this is not really a good idea. How do you expect us to generate friction in oil? And basically, our potential client said, that's your problem. We've got an issue, you need to solve it. So we eventually found that we could get the tool to embed. Once the tool was embedded, the oil was no longer playing a part in the process.
We have another comment here in the front. No?
Yeah,
No?
Yeah.
No. Oh, we have another.
Questions.
There.
Thank you for the presentation. I would like to ask, how does this process handle the joining of different materials? I'm thinking about bimetallic joining, so aluminium and steel, for example.
Normally, at a conference like this or a seminar, I bring a sample of steel that's been friction stir welded to aluminium and hand it round for people to look at, and then explain why theoretically it cannot be done. if you think about it, aluminium melts at 600 degrees or thereabouts. Steel doesn't get soft enough to friction stir weld until about 1,000 degrees. So effectively, the aluminium is now a liquid on the floor whilst you're welding to the steel. So we say, no, the theory says it can't be done. We actually can, but we don't tell anyone how just yet. It's a good point because friction stir, it can weld different grades of the same material very easily. So, for example, aluminium, if we're welding aluminium, we can easily weld a 2000 series to a 7000, despite most people telling you that individually those aren't weldable. Well, they're very easily weldable by friction stir. If the materials have a similar softening point, then you can weld different materials. So we did some work for the fine arts department of a university that wanted to weld gold, silver and copper for an artwork. And because those all soften at about 600 degrees, we had no problems welding gold, silver and copper together. We often weld stainless steel to carbon steel just to prove that we can and it looks nice. So welding different grades of the same material relatively easily. So one of our party pieces is to weld carbon steel, something like S460, to a super duplex stainless steel. When we do the weld testing on that, it tends to fail in the carbon steel in the weakest point away from the weld. The weld itself is still stronger than either of the two parents. Ultimately, we want to be able to weld aluminium to steel. That's of interest to the shipbuilding industry because they want a steel hull, aluminium superstructure. The defence industry likes the idea of welding very dissimilar grades of material together for their own reasons. The electrical industry and the thermal management industry both want us to weld aluminium to copper, basically for electrical conductivity and thermal conductivity, basically trying to reduce the amount of copper that they have to pay for. And we found that we can weld aluminium to copper. So it's a forging process. The chemical compatibility of the two metals isn't so critical. It's can we actually hammer them together? And generally, yes.
We had another question there.
Just a follow-up on your comment on when you found out you could use this process immersed in oil or fuel. So the question was, how did you find out? Was it just did you put metal to metal and go like, oh, it works, or did you have to use some type of special coating or something? Or is that something you'd rather not discuss?
No, it was relatively simple. TWI, we work for our member companies, and they came to us and said, we've got a problem. And they said, can you weld under oil? And our initial thought as scientists was, no, don't be silly. We need some friction. And their view was, we're paying you, change your mind. So we said, okay, we'll get some oil. So we put two plates of metal together, covered it in oil, had to think about how we could go about generating friction when we didn't have a friction couple. And we worked out a way to do it. It didn't involve anything really complex. It was actually much simpler than we anticipated.
So it was more procedural than...
Yes.
Oh. Thank you.
Okay, thank you. Any more questions? Now is the time. Stephen has solutions? No? So I think we can end here. It was a pleasure to be here and to present the development so far on the project. I think we all are pretty confident that soon, in 6 months' time, we'll have more developments, also from other parts of the project that were not presented here today. So feel free to follow us online on social media, on the project website, future events, and thank you so much for being here this afternoon.
Okay. First of all, thank you for your interesting presentations. This is an interesting research project with many challenges, huge challenges. And I think if you are successful, there will be a huge... When you finish your work, there will be a huge advance in this technology, and of course for the repair of ships, but also in other fields, I think. So on behalf of the mechanics specialization of the Ordem dos Engenheiros, thank you very much for the presentations and for sharing your developments inside this project, this interesting project, and thank you for the attendance in this seminar. It was also being transmitted all over the world on the YouTube from here, from Ordem dos Engenheiros. So thank you again and have a nice day.